Welcome to the Henry AI Labs walkthrough of Keras code examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun, generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. Francois Chalet has recently shared a series of tutorials on using TensorFlow Cloud with runtimes like Kaggle Notebooks or Google Colab, or even connecting to the paid Google Cloud Compute backend, as well as the Keras Tuner interface for doing hyperparameter optimization. So we have 3 tutorials, one of which is how to get started, and then 2 are examples of CFAR 10, and then another structured data classification, which is usually like tabular data. So we have 2 examples. We're going to learn how to optimize the hyperparameters of a deep neural network using the TensorFlow Cloud runtime. This is the documentation for the Keras Tuner library. Keras Tuner is a library that's built natively to TensorFlow and Keras to help you optimize or tune your hyperparameters. Hyperparameters describe the various control knobs on a deep learning algorithm, like the learning rate, the batch size, the hidden configuration of a model like the number of layers or the hidden dimension width, as well as things like the data augmentation strength, maybe SGD or atom momentum hyperparameters. There's all sorts of hyperparameters that play into training deep neural networks, and it really depends on the particular framework that you're using, how many of these hyperparameters you're going to have to deal with. But it's still really useful to get a sense of this interface with this Keras Tuner library. So quickly from this documentation, I want to present 2 things quickly. So most of these hyperparameter optimization tools, they have some kind of API to wrap in, or interface to wrap in the construction of a model given the set of hyperparameters. So in this case, we have our model builder function, and then you pass it in some hyperparameters and it'll render a model. In this case, we're using the interface of hp.in, hp.choice. These are 2 ways native to the Keras Tuner library to define an interval of values. So what this is doing is when you define this HP units equals hp.in, units min value equals 32, max value equals 512, step equals 32. As you can probably infer, it means that it's going to go 32, 64, 96, and so on, up to 512, and test these values out, searching through the different hyperparameter configurations to try to find the best amount of neurons to put in this first dense layer. And it's going to do a similar kind of search, but with much less values, as it's choosing between this set of learning rates that you pass in. So right off the bat, you can see 2 different ways of setting up the syntax for doing a hyperparameter search. This is how you do a search through integer values. It's more broadly defined compared to passing in a list of values for learning rate. So this is how you do a basic model builder interface, and then you pass it into the Keras Tuner function. So what's really exciting, they have random search, Hyperband, Bayesian optimization, sklearn. And I'm really excited about Hyperband and Bayesian optimization. Hyperband is where you have unequal resource allocation. So say you use 50 epochs of training with one configuration, then 10 for the next, then 65 for the next, and then 5, and so on. You have unequal resource allocation, and it's a really interesting idea for getting a sense of the performance of different hyperparameter configurations. And then Bayesian optimization is a more advanced technique where you explicitly have a model of the search landscape, and that's a whole video in itself. But just from this quick interface, I hope you can get a quick sense of the Hyperband, the Keras Tuner interface to when you pass in this model builder function, and then how to define the model builder function. And if you want to learn more about this, Introduction to Keras Tuner on the TensorFlow core documentation. Hopefully that was a decent introduction to Keras Tuner, looking at the TensorFlow documentation. Here are the notebooks authored by Sina, Chavoshi. This is the username if you want to follow on Kaggle. These are the notebooks that have been recommended by Francois Chalet on Google Cloud runtimes and the Keras Tuner interface. So now let's go through them. Quickly, it starts off with the Google Cloud platform. So as you sign up for Google Cloud, you get a $300 credit. So you can still play around with $300 of computing credits before actually putting your own money on the line. This line of code is just pointing to when you set up your Google Cloud project ID, you're going to get a project ID and you're just going to put that in right here. So that would be going to this link and then filling out the form to start your Google Cloud account, and then fill out and probably give some details about your project ID. So the next task is to enable Google Cloud Software Development Kit and authenticate your notebook. So what we do now is we have three kinds of notebooks. Okay, so this is depending on how exactly you're going to do this. So do you want to use Kaggle notebooks, Collab notebooks, or the Google Cloud Compute AI notebooks, or probably the more powerful ones, but also more expensive ones. So if you're using the Kaggle notebooks, then this is what code you need to do in order to pass in the Google Cloud credentials with this project ID. So you just loop through this, and no need to change any of this code. The only code you need to change is putting in your own personal project ID from filling out this form to start your account. So then you do a similar kind of interface with Google Collab. Google.collab, import authentication, auth.authenticate user. This looks pretty native. It doesn't look like you're doing anything that is outside of the normal for Google.collab and the collab runtime. So then step 3, so if we are going to be trying to really use some serious computing power, we're going to need to have a billing account and put the credit card on file, and this can be a bit intimidating, but I think generally it charges you for the hour, and my personal experience is it's been getting easier and easier to call customer service or have a chatbot and avoid spending too much money on cloud runtimes. So once you've set up a billing account, you're going to have to install this with the shell command in your cloud notebook runtime, gcloud beta billing accounts list, and then you'll use this will present you with where your billing account ID is, and you'll grab that, copy it, paste it, and put it in here, and then another shell command will link this runtime with the billing account. So the next step is to use these two specific APIs, AI Platform Training Jobs API and Cloud Builder API, and we're going to use this just with this shell command. Again, you can just copy and paste this. There's nothing that in this particular shell script that's particular to your IDs or any credentials like that. So the next step will be to create a Google Cloud storage bucket that's going to help us store temporary assets, particularly the model checkpoints. So during deep neural network training, especially with hyperparameter tuning, we're going to be searching through many different configurations of the deep neural networks. We may have one with 8 layers and a 512 dimension hidden vector, or 12 layers and a 256 dimension vector, and we're going to want to save and checkpoint these model weights so we can load them later and not waste our time and our money when we are doing this at scale with a credit card on the line and a Google Cloud Compute backend. So we're going to make sure we have a Google Cloud storage bucket so we can save our model weights. The final step of getting set up before we get started with our CFAR 10 and structured data examples is to set up Cloud Tuner. So again, this is just a series of commands that you can just run. Service account name, you run your service account, and you just fill out a form here to get this information, and then you can really just run this code. It doesn't look like there's anything really to be too worried about or interested in with respect to just kind of copying and pasting these commands to get it connected to your runtime. And now overall we have the Cloud Tuner, we have a Google Cloud Storage bucket, we have these APIs of the AI Platform Training Jobs, we just initiated the Cloud Builder API, and we have the link to the billing account and the authentication with our Google Cloud ID from the very beginning and with our project ID. So with this first notebook, Google Cloud Project Setup Instructions, we're ready to get started with our CFAR 10 example and our structured data classification. Before diving into the Kaggle notebook, this example from the Keras Tuner documentation is very similar to when we looked at the TensorFlow Core Keras Tuner documentation, and it'll give us another sense of having a succinct block of code to wrap the idea of Keras Tuner. So we have import Keras Tuner. This is the Keras Tuner library. That's the focus of this tutorial. And then we're going to be having our model building API and then our Keras Tuner function call. And the rest of this is just loading the data, pre-processing data. This is all just loading the data from TensorFlow datasets, pre-processing it, so it's between 0 and 1, and then the dot map, so we pass this function in, cache, batch, shuffle. So this is all just standard loading the data from TensorFlow datasets. So then we see tuner.search. This is when we do the function call on our Keras Tuner, where we're telling it here's the data set, here's the validation data, and here's the callback to early stopping. Early stopping is where, say you do 20 epochs and then 25, 30, and then the accuracy isn't changing. You just cut the training because that model probably isn't going to improve on its own. So we have at the end of our tuner.search, we can index it by doing best model equals tuner.get best models, best hyperparameters, tuner.get best hyperparameters. That's how we return the output of this hyperparameter search. So we see again how we do the hyperparameters. We have hp.init. We're looking for convolutional blocks, the number of filters in these convolutional blocks. We're looking for the pooling choice between average pooling or max pooling. We're looking at the hidden size of the next dense layer between 30 and 100 with step sizes of 10. And then we're looking at the dropout parameter, with this hp.float. So here's a new one that we haven't seen yet, is passing in the float value rather than ints for these hyperparameters to search through. Similarly, instead of doing hp.choice that we saw in the documentation, now we're using a range of values for learning rate, and we're passing in the hp.float. So here's another example quickly before we dive into the Kaggle notebook of how to use the Keras Tuner with CFAR10. We have the build model API, the call where we pass in build model, the objective, the number of epochs for the maximum runtime of any one hyperparameter configuration, and the hyperband iterations. Because hyperband is a stochastic algorithm, so we're going to want to run it a couple times in order to get a better estimate of the overall hyperparameter performance. So now we're back in the example of hyperparameter tuning CFAR10 using Google Cloud. The first set of commands is just importing basic libraries. Then we pass in the Google Cloud project ID that we defined previously, our service account name, all the previous things that we defined in the last notebook with the storage bucket and all that. So the next thing is now we're going to have a name for the job. So we have CFAR10, and this is used in the file path for indexing where we're saving our weights in our Google Cloud storage bucket. So this is the last block of code we need to get up and running with the Google Cloud runtime with Keras Tuner. So we just run this same Authenticate user thing that we did previously, and now we're running, and whether this is running in a Kaggle notebook, where you would run this one, or if you're running in Google Colab, you'd run this one, and now we're up and running with our Google Cloud Compute backend with these Cloud Notebook interfaces. So now we load our data. We have the CFAR10 dataset that's built into Keras compared to last time when we saw the TensorFlow datasets, tfds.load. This is just another way of getting the CFAR10 data. And now again, we see the way that we're initializing these hyperparameters and passing them into the model builder. So this time we're seeing a slightly different syntax for doing this. Rather than doing def build model HP and then doing hp.in, hp.float, and so on within the loop of the model builder, now we're defining the hyperparameter ranges outside of the model building, the build model function. And this is really useful. It's really common to see people do this with, say, YAML files, YAML configuration files, where they define these kind of things, and then you would load it in and pass it to this kind of interface like this. So it is kind of better practice to define your hyperparameters outside of the actual build model loop that you're going to be passing into the Keras Tuner. So in this case, we have a similar idea: the conv blocks, the number of blocks of convolutions, the filters, the pooling in these convolutions, the hidden size of the dense layer connected to the output of the convolutions, the dropout regularization, and then learning rate. These are all just some of the hyperparameters of just an average convolutional neural network. So already you can get a sense of how many hyperparameters are involved with training deep neural networks, especially with these cutting edge research ideas. So similarly, just instead of hp.in, it's hp.get, and then you just sample from the set of hyperparameters defined in this object, keras.tuner.engine.hyperparameters, the hyperparameters constructor, and then we define it like this. So this is another way of doing it. This is much cleaner. I highly recommend doing it like this. This kind of syntax of defining your hyperparameters and then passing them in this way, this will probably scale for you much better than something like this, where you're trying to define the hyperparameters within the model builder loop, just with respect to having a cleaner interface and for sharing the hyperparameters that you're tuning with whatever team you're working with. So now we have another interesting difference in this code compared to the original Keras Tuner example. In this case, we're using the Cloud Tuner. So we do from TensorFlow Cloud import Cloud Tuner. Instead of doing Keras Tuner, we do tuner equals Cloud Tuner. We similarly pass in the build model function, but we also pass in the project ID, the project name, the region, and then also we have our distribution strategy. So this is for using 4 GPUs. So this is a really exciting idea, using 4 GPUs. You probably will need to pay a little money to be using 4 GPUs. Luckily, you do get $300 of Google Cloud credit if this is your first time using it. So the tf.distribute.mirrored strategy, I wouldn't read too much into that. It's just one of the ways of doing this distributed optimization with 4 GPUs and doing this hyperparameter optimization. It's likely that probably the implementation of this is each model runs on 1 GPU at a time separately. It's probably not like sharding the model across 4 GPUs, or even having some kind of partition where you have 2 models on the same GPU. It's probably safe to say that it's implemented with 1 model on 1 GPU at a time. But you imagine how much faster this is going to be for hyperparameter search, as you can send different hyperparameter configurations to the 4 workers instead of just 1. We've defined our model builder function that renders a model given these hyperparameters. Then we've initialized our Cloud Tuner function with the build model, and then the different parameters on where in Google Cloud Compute we have access to running to a runtime where we can run these experiments. And now we're going to set up the remote training with the TensorFlow Cloud runtime. So previously we had imported TensorFlow Cloud, aliasing it as TFC. So we're doing tfc.run. We're indexing our TensorFlow Cloud library and doing that kind of runtime on the Google Cloud Compute backend, and we're watching it on our front end of the Google Colab or the Kaggle notebook. And there are some additional requirements TXT. This is if you're not doing it like that. So if you have a different kind of image with Docker containers, and I don't know too much about that, but if you're running it on something other than Google Colab or Kaggle notebooks, I'd be mindful of what this is trying to do. So this is how you initialize the Cloud Tuner, and then it's going to run the job, and you'll be able to monitor if you like by looking at the tensor board, because we passed in this callback that's telling it to log the validation accuracy as it's searching through hyperparameters with the tensor board visualization interface. At the end of the training, we can index our best models with tuner.getBestModels, tuner.resultSummary, and tuner.getBestHyperparameters. So all in all, this is what we need to do in order to set up the basic CFAR 10 using Google Cloud. So first we set this up by using this set of installation instructions. We pass in these required parameters and IDs and access codes to our notebook, and then we'll run this basic hyperparameter search. And probably what's most interesting and customizable to your problem is this block of code. This is probably the only block of code you really need to pay attention to and actually change any of the code. I'd really recommend just probably copying and pasting everything else, but this block of code is where you're building the model and passing in the hyperparameters. So this is really the one to pay attention to, is this block of defining hyperparameters and then your model building API. The rest of it is just kind of plugging it all in together and getting it to run, but it's mostly kind of like boilerplate code of putting in the basic. I don't think there's any room for improving or customizing. Maybe you could have your own separate callbacks, put in your own data set, maybe change this, but so on. But this is the meat of it. This is what to pay the most attention to. So now we're in the other notebook, hyperparameter tuning wide and deep model using Google Cloud with a structured classification data set. So this is very similar to everything we just did with CFAR 10. The key difference is that it's a different data set. So where we have the difference is that we're loading in this data set from the Kaggle competitions API. So this is a dog food day. I don't personally know this data set, but this is just an example of using another data set instead of using, say, tf.keras.datasets.cfar10 or tfds.load.cfar10. This is how you would use another data set, integrate it with this syntax if you're using this for, say, a Kaggle competitions. So you can do shell script Kaggle competitions download and then have this data set. So personally, I really love the Kaggle shell script for getting data into, say, a Colab runtime or a Kaggle notebook. Well, obviously, but getting it into the Colab runtime particularly, I really like using this shell script Kaggle competitions or Kaggle datasets download, and it's really easy to get data into your runtimes to do machine learning with. So this is all just pre-processing where you have a CSV file, you use pandas to read the CSV, you use the scikit-learn train test split to split this data from the pandas data frame. You use df.dataset, this is defining a function to go from a pandas dataset to a TensorFlow data.dataset object. Use the syntax of first splitting it into the labels, and then you do from tensor slices, where you can say pass in, from tensor slices you could pass in like a NumPy array, or you could pass in whatever, this like a list. From tensor slices is a really nice interface for going from most ways that machine learning datasets are structured into these TensorFlow.data objects. And the TensorFlow.data objects are useful because you can do the shuffling, the batching, .map, all this kind of optimization under the hood once you have it in this object. So then we pre-process the data. We have just more about just converting the type, setting up this input layer for our Keras model. We have this way of setting up the numeric inputs and normalization layer. This is all just things particular to working with tabular, like CSV, row column structured data. So finally, we have the processing of categorical inputs. Categorical inputs are things like one hot encoded vectors, where we have object categories like 1000, 0100, and so on. And we have this kind of encoding that we use. You might have a data set where you have like there are string values that represent the unique class labels, and you do this kind of pre-processing to turn it into one hot encoded vectors, and then so on, the category encodings. This isn't the tutorial, the subject of this video, but here's the thing that we're interested in. Now in this thing, we're back to our create the model interface. In this case, instead of calling it build model, we're calling it create wide and deep model with our hyperparameters. Again, this is the syntax for defining the hyperparameters. Really great organization of code, design patterns to have the hyperparameters here in a separate file and then passing them in as an argument to the model builder in our hyperparameter search API. So with that said, the rest of this is pretty standard, nothing too different from our CFAR 10 example. So just showing a little bit of a difference on really just showing that you can do this with other kinds of data. I don't think it's really, or just maybe a quick example of without doing convolutional blocks. You see how in this case you're just searching for learning rate and then the number of layers in a fully connected dense model. You can imagine searching for transformer hyperparameters, all sorts of things. So really, I think just what this is adding is just this sense of broadening your scope of what you can use this for. But you see really the code is like basically the exact same. So to wrap it up, I'm really grateful to Francois Chalet for sharing these awesome notebooks and learning a little more about how to use the Keras Tuner API with Google Cloud Runtimes. I think this is pretty easy to set up. A really great example of how to set it up on the back end of Google Cloud Compute Platform. And then I think the biggest takeaway from this is understanding the interface of defining hyperparameters, understanding how to build models in this function and pass these functions into the Cloud Tuner runtime. So really great tutorials. Also recommend checking out Introduction to the Keras Tuner to learn more about it. And this quick example, again, I don't prefer this syntax of defining the hyperparameters within the build model loop, but it's another way of doing it, and it's a quick, only 61 lines of code to get a sense of how to do this. So thanks for watching, and I hope you do something interesting with this information on how to use the Keras Tuner and the TensorFlow Cloud runtime.